We'll start with the first lecture that will be oriented to how you can make energy savings inside buildings and how this relates to different automation systems inside the buildings. That can be very, very useful if you want to couple um, lighting control systems with centralized building management systems. Then the second lecture will be more oriented on the standards for lighting, and this afternoon I will show you another aspect, which is when you want to light up something, a room, a class, a parking, I don't know what are the requirements and how you can evaluate what kind of lighting you need for each space. And finally, tomorrow we'll speak about effects of lighting in energy and materials. We speak mainly, I don't know if you never had the opportunity to work with, we'll speak about life cycle assessment, which is a standardized method to evaluate impact of different systems. Okay. Okay, let's start then. Well, come up. Okay. Lighting and buildings, energy and automation. Well, as I told you, lighting use huge quantity of energy worldwide, and globally worldwide, almost half of that energy is used for lighting up buildings. Well, there is the place to make substantial energy savings and protect also our planet. Well, you can do that passing through controls, as have been explained at the beginning, installing energy efficient systems like LED lighting inside the buildings, and associate sensors and controls, and then connect all that in global networks. There is a first slide here explain why, because the goals of including controls, you understood that, is playing with the use time of the lighting system or any other lighting system. And generally, when you have automation systems inside the buildings, you can reduce the energy consumption, you can improve, of course, the end user comfort, and also improve security, because this kind of systems can control also the access and reduce also the installation cost. Reduce installation cost maybe implies that you increase the maintenance cost. But if the system has survey functions of the operation, and also you can couple in some case some self-healing functions, then you can even reduce maintenance, but then the initial cost is much higher. You can see here inside buildings, I told you that half of the energy used for lighting is used in buildings, but when you look what happened inside the buildings, you see that the potential gain, if you play with the thermal regulation and insulation of the walls, you can go up to 25% energy savings. If you use very efficient heating systems, well, here in India, especially in Nagpur, you don't need that, but if you go in the north, most probably yes. If you use efficient heat pumps, you can go up to 70% of energy gains. If you play with the blind controls, you can go up to 32% of energy savings. Why? You tell me the blinds has to do something with energy. You will understand that just after. Lighting is the champion. You can achieve up to 58% of energy gains playing with building automation. And finally, um, ventilation and air conditioning has also a relatively large energy gains potential. Well, how lighting influence the whole building? And now you understand why blinds are very important, because when you have a place that is occupied by humans for a given activity, then you have openings, can be windows, can be doors, can be roof openings, roof lights, and of course you have also artificial lighting inside. You have lamps, and what happened? The sun sends a lot of daylight during the day, but the daylight, remind, is in a large part infrared, and this infrared penetrate also the premise. The lamps, they have to evacuate heat. I remember you that up to 75% of a white LED system, the power entering to the lamp has to be evacuated by heat. Then you have the equipment inside the room. You have the occupants. Each one of us, we are the equivalent of, if I'm correct, 100 watt machine, and we radiate also. And finally, you have exchange between the walls and the external area, and that means more lighting you install, or more daylight with infrared you allow penetrate in the room. Higher is the temperature, and higher the temperature, more air condition you need to evacuate the calories. You see, everything is interconnected. If you put good insulation here, or if you put automatic control blinds, you can cut some part of the radiation coming in, and with insulation you can get also less heat coming from outside. The problem is, if you have very good insulation, if the temperature inside decrease, it will be difficult also to evacuate the inside temperature. Well, globally, lighting has a lot of potential, because when you play with lighting, either daylight or artificial light, finally you impact all the other systems. Okay, the question is how you can measure the lighting energy, and how you can do it to a standardized way in order to speak always about the same stuff at any place, at any kind of building, whatever is the use of the building, whatever is the number of people inside. Okay, of course, we are engineers, electrical engineers. If I tell you how use the energy, I show you the very simple equation is power, install power. I count how many lamps I have. What is the input power? I add the parasitics, what the driver can use, what the sensors can use, plus, of course, multiply by the time, okay? Yes, but this is not so easy, because this is for a very simple system with just lamps and on-off switches. What will happen now if you start implement sensors? Sensors that they switch on and off the light, or sensors that they reduce the light following the situation. And then you will see that you can write the equations, no problem. They are rather simple, but they are completely different from one building to the other, because it depends what you install additionally. Well, we had to look about standard methods in order to evaluate the energy consumption for lighting inside the buildings, and I will show you here two methods. One is the French one, and the other is the European one. That allows you to calculate the energy consumption, standardized way, and then you can compare comparable things. You cannot compare apples with pears. Well, the first way to do, the French one, is calculate the consumption for lighting. It's given by a factor multiplying here the weighted consumption for lighting in kilowatt hours per year, and then you have the number of kilowatt hours, and behind here you have the operating time. Okay, this is kilowatt hourly consumption. Sorry, kilowatt per hour for 1 hour, and the 2.3 in the front. This is very specific. It depends on the country. This is for France the factor that allows to pass from primary energy to electricity. Electricity, to produce electricity, you use oil or thermal production of energy. France uses a lot of nuclear and so on, renewables. And these factors say you that 1 kilowatt hour charging your car or illuminating your building or powering your air condition equal to 0.3 kilowatt generate power. And this way here is given by not a standard, it is given by the law. The French law for building construction include that we call the thermal regulation principles, who are written in the law. And the law says if this value here is above a fixed figure, that can be, for example, more than 5 kilowatt hours per year and per square meter for offices, then your building license to build the building can be denied. You have, before building the building, to calculate how much energy this building will spend, and if you are above some limits, then the government, the regional or national government, can deny the license to build, the authorization to build. Well, then the question is how you calculate that, the famous weighted consumption, and there is also inside the law and the explanation of law, there is the way to calculate that. You can see here is given by that equation what you have. The weighted consumption in 1 hour is here the surface density of installed power in kilowatt per square meter. But to calculate the number of square meter, you don't just take the surface of that area, but you have to use only a part of the building. For example, the law says when you have less than 2 meters high between the roof and the floor, here, for example, the small blue places, then this part is not counting for the surface. Indoor parking space, they don't counting. Underground spaces, they don't counting. And so, well, you have really to understand the law and read all what you need there in order to be able to calculate the surface. Calculate the power, global power, again, is not a problem. Number of lamps multiplied by the installed power, but then here you have to multiply by that. And then you have to take into account the useful surface with all the explanation that I put here. And finally, you have here 2 corrective coefficients that they are taking into account any kind of control functions. For example, you see that the first one, this one, if you have just a simple on-off switch, the value is 0.9. But if you have a presence detector, the value is 0.7. That means if you put presence detectors, this value will be 30% lower. and if you are in the limits to get or not the authorization to build your building, the only option that you have is to include sensors inside. Otherwise, you will don't obtain the authorization. And this one, the second, this one is taking into account how much daylight, that means free light, you can use inside your building. And you see here the value may change between 0, 1, 0, 3 up to 1. If you have very few daylight, especially if you are inside the building in premises that they don't have access to direct daylight, then the C1 is equal to 1. This is the highest value. But now if you have a little bit daylight up to 500 lux, and you add the dimmers, then this value goes from 1 to 0.1. You divide by 10 the standardized coefficients for the calculation of the consumption. This is an E missing here. E is the illuminance. That was the French method, which is rather complicated, but it is an obligation. The RT laws, thermal regulation, exists since 2007. It is an obligation to respect it, and it has been revised in 2012 and again in 2020, and will be revised maybe later on also. This is the European matrix that we call the LENI, the Lighting Energy Numerical Indicator, which is in fact very similar to what we have in France. Is the energy used for lighting. Oh, he stay in French. I will divide by the illuminate surface, but here we speak in all the surface. We don't have tuning. Energy over surface, and the useful energy is defined that way. Is the installed power multiplied by the user's time in hours per year. This one is kilowatt, and here you have a number of coefficients, corrective coefficients like in European regulation, plus the parasitics. Your system use say 100 watt to produce light, but you add a sensor that can use 1 watt. You can add a driver that consume 1 more watt and things like that. This is the parasitic energy that is associated to any other components of the system related to lighting. The 3 factors here is very similar to what we have in France. F0 is the occupancy factor. This is the energy saved by automatic control systems that turn on and off the light when the rooms are unoccupied. I will show you how it works. FC here is the illuminance constancy factor. This is something that we don't take into account in France. This just remind, I told you that what is the lifespan of the lamp is the initial value of the flux, and this flux is degrading with the time. In France, we consider that the flux is the same all way to 15, 20,000 hours. The European metrics add a correction here, and finally FD, the last one here, is the natural light availability factor. It depends on the orientation of the building, it depends on the surface of the windows and things like that. And finally, then you can calculate the value of LENI, which is given per kilowatt hours per square meter per year, and this is regulated by European regulation EN 15193, which is a European directive, and the European directive has force of law for all European countries. That you have to understand here is either using the French method or the European one. As lower are those coefficients, LENI in Europe or the CEP in France, lower is the energy consumption for lighting. And you can say this room here with those lights, I have a given Lenny. I will show you examples. If I change my system and I add that, and that, how much is my Lenny, the new one? And then you can say, okay, I have 20% less Lenny. I save 20% energy. Well, energy savings can be achieved by different ways. The first one is to use high performance equipment. This is the technology, high performance lamps, LEDs, and any other device that you have inside, for example, drivers. Use of the technology, that means you can start with rational use of the technology and the light. You can add timers and controls, sensors, and intelligent systems. You can explore the human visual abilities, and more especially this for cities, the mesopic vision. That was possible with discharge lamps. Is much more complicated with LEDs, but we don't speak about that because this is for outdoor. And of course, indoor, you can use as much as natural lighting when possible, but always taking into account that a natural light may have some problems like glare or bringing also additional